Hey everyone, let's take a look at number 6 in section 4.6. We are going to consider this function here, 4x times e to the negative x squared. And we're going to identify the locations where f has transition points. And we're going to do other things. They have prompts for you to give basically where we have local max, local min, and points of inflection. By the way, transition points are points in the function where we have either a local max, a local min, or an inflection point, or basically anytime we have a change in shape of the graph, but those are what we're going to be looking for. Just off the bat, what's the domain of this function? Well, as you see me written here, I've written here, it's all real numbers, right? Because, the domain of the exponential function is all real numbers. Even though I got a negative here, e to, any negative power is always a real number. So domain is all real numbers. And how do we proceed? Well, we start off with the derivatives, and then I need the derivative of the derivative or the second derivative. But let's start with the derivative. Notice I'm going to have to use a quotient rule because I got 4x times e to the negative x squared. So a lot of you kind of forget about the product rule. Do not forget about it. You just can't take 4. You just can't say this is derivative of 4x is 4, derivative of this thing, and multiply them together. You have to take the derivative of 4x, which is 4, times e to the negative x squared, plus 4x times the derivative of e to the negative x squared. Now, what's the derivative of e to the x squared? Well, that is a chain rule, right? It's not the derivative of e to the x. So remember, if I have the derivative with respect to x of e to the u, the derivative of e to the u, right, outer function, times the derivative of the inner function, right? Well, what's the inner function? Negative x squared. What's the derivative of negative x squared? It's negative 2x. So I get negative 2x times e to the negative x squared. Negative 2x times e to the negative x squared. So this is chain rule. Okay, so you've got to know how to do these rules. Product rule, chain rule. You got to know quotient rule and the rules for all the derivatives of those trig functions. Okay, and other functions. So they'll come up. Okay, so we have 4 times e to the negative x squared. Here I get negative 2 times 4 is negative 8. Notice I've got an x here and an x here, so there's an x squared, e to the negative x squared. So here's my derivative. I'm going to use that to find my second derivative in a minute, but I'm going to go ahead and factor this because I want to know basically when is the derivative either 0 or undefined, so I can talk about transition points. Possibility of transition points. So best way to do that is to factor this expression, and I can factor out a 4 and the e to the negative x squared. That leaves 1 here. Factoring a 4 out of 8 leaves 2. E to the negative x squared is pulled out. I'm just left with the x squared. So this factors this way. Now, notice this expression is defined for all real numbers x. It's never undefined. I'm never like dividing by 0 or taking the square root of a negative number. But when is it 0? Well, e to the negative x squared, that is always greater than 0. So this right here is always greater than 0 for any value of x. It's never equal to 0, never negative. But 1 minus 2x squared could be 0, and that would make the derivative 0. And that's going to be true when 2x squared is equal to 1, or when x squared is a half, or when x is, don't forget, plus or minus the square root of 1/2, or 1 divided by square root of 2. Now you can also rationalize this, multiply top and bottom by square root of 2, and this is plus or minus root 2 over 2. I'm not sure if Achieve, will take either, we'll want this one over here on the right or this one. This is fine for me on a test or something. Okay, that's just the first derivative, right? And these are potential transition points. They're potential points of change from increasing to decreasing or decreasing to increasing. And we'll do that in a minute when we look at a sign check of the derivative. Okay, second derivative. I'm going to take the derivative of this function here. So 4 is a constant multiple. What's the derivative of e to the negative x squared? We just did that here. It's negative 2x e to the negative x squared. Okay, minus 8. I'm going to pull the 8 out. And then what do I have? X squared times e to the negative x squared. So like I started with, right, this is a product rule. So I have to take the derivative of x squared, which is down here 2x, times e to the negative x squared, plus x squared times the derivative of e to the negative x squared, which is negative 2x e to the negative x squared. Okay, so I've got 8 in parentheses times all of this. let's clean this up, right? This will be plus what? -2 x squared times x cubed e to the negative x squared. Now, let's simplify. Distribute here, well, multiply by 4. I get -8. 4 times -2, -8 x e to the negative x squared. Distribute the -8. -8 times 2 is -16 x e to the negative x squared. And then -8 times +2, sorry, -8 times -2, +16 x cubed e to the negative x squared. Notice these two here are like terms, so I can combine them. -8 minus 16 is -24 x e to the negative x squared. So here's my derivative of my derivative, my second derivative, right, for the function. And I'm interested, when is the second derivative 0? And so I'm going to factor this. I can factor out from the -24 and 16, I'll factor out a -8 just because there's a negative here. Factor out a -8. And then I've got an x and an x cubed, so I can factor out an x. And I've got e to the negative x squared, e to the negative x squared, so I'll factor that out. So what's left here when I factor out -8 from -24 leaves me +3. I've got my x and e to the negative x squared already factored out. And then pulling a -8 from a +16 leaves a -2. I pulled one x out of the x cubed, leaving x squared, and I pulled the e to the negative x squared out. So here it's factored. Now, when is the second derivative equal to 0? When it's equal to 0 if x is 0. Notice I've got an x here. I did not have that up here, right? Certainly if x is 0. So don't forget that x could be 0. E to the negative x squared, again, this is never 0. This is always positive, so we don't have to worry about that. And then 3 minus 2x squared, well, that could be 0. That's going to be true when 2x squared equals 3, or when x squared is 3/2, or when x is plus or minus the square root of 3/2. Okay. There's the potential points where our second derivative, those are the points where our second derivative is 0, and those are potential transition points. How do we know for sure? Well, we're going to now do a sign check for my first derivative and my second derivative. Remember, the first derivative is 0 at these 2 points of x. Second derivative is 0 at these 3 points, right? 0 and plus or minus square root of 3/2. So I'm going to do a sign check on things, and I'm going to do it all at one time. You could do it separately or whatever. Just kind of, I like to put it all together. It helps. So here's my real number line, and these are all the important points. Remember, let's do the sign of the first derivative at -1 over square root of 2 and +1 over square root of 2. 1 over square root of 2, by the way, is about 0.707, just for reference, right? The first derivative is 0 at both of those points, and that's what we said, right? At these two values of x, the first derivative is 0. So now I just want to do a sign check. And so you just want to plug in, like if I plug in 0 into my first derivative, and I can do it, let me do it in this factored form. Of course, remember, e to any power is positive. So this part right here is always positive. But if I replace x with 0, this is 1 minus 0. I just get this is positive number times 1. It's positive. So if I plug in 0, I'm getting a positive number. So notice the derivative is positive in between -1 over root 2 and +1 over root 2. If I plug in something bigger than 0.707, like 1, I'm going to get a negative value for my derivative. So going back to the first derivative, I plug in 1. Again, this is positive. 1 minus what? 2 times, plug in a 1. 1 squared is 1. 1 minus 2, -1. So negative times positive, I get negative values. Well, same thing if I plug in something like -1, something less than -0.707. And -1, since I square this, is +1. I still get 1 minus 2, -1 here, times a positive. So there's the sign check for f prime. What about f double prime? Remember, it is 0 at 0 and plus or minus the square root of 3/2. Square root of 3/2 is about 1.225. So it's 0 at plus or minus square root of 3 over square root of 3/2 rather, and then also at 0. And then I just plug in values. Like I can plug in something greater than 1.225, like 2. If I plug in 2 into this, so be careful here. It's -8 the way I have it. X is 2, so this will be a negative number, -16. This is always positive. But if I plug in 2 here, 2 squared is 4, 4 times 2. This is 3 minus 8. This is going to be a negative number. So negative times negative is positive. Okay, now I'm doing all this reasoning. If you just want to use your calculator and just plug in a number bigger than 1.225, like 2, just plug 2 into this, or even the unfactored form. Doesn't matter. Sorry, yeah, the second derivative here. So just plug it into here or in here and just get the output. It doesn't matter the value, just so much what's the sign. Is it positive or negative? So you have to be able to do that or reason. Okay, so I'll just let you check the rest of that. If you do, your second derivative is negative for values less than negative square root of 3/2. It's positive between negative square root of 3/2 and 0. And then it's negative between 0 and positive square root of 3/2. Just putting this together, we talked about this in the lecture, right? The shape of f, right? We use this notation of minus minus derivative, first derivative negative, second derivative negative means what? First derivative means negative, means we're decreasing. Second derivative negative means we're concave down, decreasing, concave down. Minus plus means decreasing, concave up. So this shape. Plus plus, increasing, going up, concave up. Plus minus, increasing, concave down, increasing but concave down. Minus minus, decreasing, concave down, and minus plus, decreasing, concave up. So you can almost see the graph. If you just take these pieces and click and drag them and connect them into place, you're going to get that the graph of the function. Okay. All right. We now can deduce that all of these are transition points, because basically what's happening from our first derivative, we see at 1 over the square root of 2, the sign changes from positive to negative. So we're increasing here, decreasing here. So going up and going down. What do we have? A local max at x equal 1 over square root of 2, or as I said, square root of 2 over 2. We have a local minimum where the sign changes of the first derivative from negative to positive, right? From decreasing to increasing. So we have a minimum at negative 1 over square root of 2. And then notice second derivative, we have a change in sign at each of these points: 0, negative square root of 3/2, positive square root of 3/2. So all those are going to be inflection points. Notice we have to have a change in sign. So just because the second derivative is 0 doesn't mean you have a point of inflection, because it could be plus here, right? But we're changing concavity, and so all of those are points of inflection. Achieve wants you to list those with a comma separated by each one, so you can't use the plus or minus like I do here. So make sure you list each one separately, separated by a comma. Okay, now where is the function increasing? Where the derivative is positive here. So between these two values, and you want to use the exact values. So in interval notation, this is the interval it's increasing. It's decreasing where that first derivative is negative. And so for values less than negative 1 over square root of 2, so negative infinity to negative square root of 2 over 2, or 1 over square root of 2, either way. And then what? From square root of 2 over 2 to infinity, right? It's negative again, decreasing. Okay, and that's consistent with where our local max and mins are located. The function is concave up when what? The second derivative is positive, meaning the first derivative is increasing. So it's concave up when it's positive here, from negative square root of 3/2 to 0, and from square root of 3/2 on, or square root of 3/2 to infinity. And then concave down on the other intervals, where the second derivative is negative. Okay, so these are all the things that you're plugging in, so you have to be careful to do those correctly. Now, there's one other thing to check, well, and then sketch the graph, which is pretty easy. Is there a horizontal asymptote? Remember, horizontal asymptotes are what's happening to the function as x gets large in absolute value, going to either positive infinity or negative infinity. And in this case, let's look at the limit at x goes to infinity of our function. Okay, to help us out here, I'm just going to rewrite 4x times e to the negative x squared is the same as 4x divided by e to the positive x squared. And the limit as x goes to infinity now, 4x is going to infinity, and e to the x squared is going to infinity, right? Since x squared is going to infinity, e to the x squared is going to infinity. And guess what? This is L'Hopital rule form, right? So this is L'Hopital form. And so we're able to use L'Hopital's rule to evaluate this limit, or try to at any rate. Notice I put a little L over here when I'm using L'Hopital's rule, equals limit as x goes to infinity. Derivative of 4x is 4, And the derivative of e to the x squared, well, it's 2x e to the x squared. That's the chain rule. We talked about that basically previously, just a minute ago. Okay, but as x goes to infinity, the top is staying at 4, and x times e to the x squared, that's going to infinity, right? 4 over infinity, that's going to 0. Right, so the limit is indeed 0, which tells us that the function f of x has a horizontal asymptote of y equals 0. And it's only one horizontal asymptote. If I change this to minus infinity, I would basically go through the same thing, and down here I would still going to 0. Okay, even though it goes to minus infinity, because x squared here, the exponent on e is still going to go to infinity, even though I plug in negative numbers going to infinity. So one horizontal asymptote. And an equation of the horizontal asymptote is always y equal, right? In this case, y equals 0. So the graph is going to approach the x-axis. So to graph it, you just need to push in those, type in rather the function into the box. And so let me just show you what that would look like real quick. Something like this on the screen here. You can see, you just type in the function and you can confirm. It's kind of hard to see. You zoom in a lot in and out and you can see what's happening, but you can see clearly we have a horizontal asymptote of y equals 0, because as x gets large, we rapidly look like we approach the x-axis. We actually never touch the x-axis here. It just gets closer and closer to it. And same thing here. Okay, and you can see the shapes. If you go back and look at what we said, there was a local maximum of at x equal 1 over square root of 2, which is about 0.707. And you see that happening right there as our local max. And we had a local min negative 0.707 about. Okay. We had point of inflection at 0. Notice we're changing from concave up here to concave down. So there's that point of inflection. And then we also have points of inflection at negative and positive square root of 3/2, which is about 1.225. And you can see somewhere in here, we're changing from concave down, and here we're concave up. Excuse me. And same over here, concave down to concave up. Okay. So there you have all the pieces. You can also check, where we said it was increasing between negative, basically 0.707 and positive 0.707. We're increasing, decreasing from 0.707 to infinity. And the concavity on those intervals, all those things are checking out. And even the shape that we described for each section is true. So hope this helps and clarifies things on this problem. There's a lot going on. These problems take some time. And so please let me know how I can help.